Welcome to the webinar, Understanding Radioactivity Through the Exploration and Mining Cycle, sponsored by CIM Magazine and Saskatchewan Research Council. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine, and my co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Just a little housekeeping before we get started. If you joined by computer audio, please make sure you've selected the computer audio button. If you joined by phone, make sure you've selected the phone button. If you have any questions during the presentation, type them into your GoToWebinar control panel question box, and the questions will be held until the very end. Now I will turn the presentation over to Ryan to introduce today's presenters. Thank you.
All right, well, thank you very much, Michelle, and thank you everyone for being here today. Today's presenters are Jeff Zimmer, who is manager for SRC Environmental Analytical Laboratories, and Stephen Crichton, who is a research scientist at the Advanced Microanalysis Center, which is also part of the SRC Geoanalytical Laboratories. So with that, please go ahead, Jeff.
Okay, let's see if I can connect. Okay, are we showing, is my screen up there? Can't tell.
Yep,
Yeah.
you're good.
Yes.
Okay, perfect. All right. Well, thanks a lot, Ryan and Michelle. And we'll get started here. As they mentioned, this is the presentation, Understanding Radioactivity Through Exploration and Mining Cycle. I'm going to talk a little bit, sort of an overview of, the whole thing, and then turn it over to Steve, and Steve will focus in a little bit more on the exploration side of things. So first of all, I'll begin with the land acknowledgement. So we're presenting from Saskatoon here today, and that's where SRC's headquarters are, and that's situated on Treaty 6 territory in the homeland of Métis. We also have offices in Regina, which is on Treaty 4 territory in the homeland of the Métis, and we also have the Cleanup of Abandoned Northern Sites project, or Project Cleans, which is in northern Saskatchewan, situated on Treaty 8 territory in the homeland of the Métis. So Saskatchewan Research Council is Canada's second largest research and technology organization. And we support industry and government and communities in a variety of projects, basically bridging that gap between academia and industry to help bring technology to the world, I guess. And we are, of course, Saskatchewan Research Council, so we are located in Saskatchewan, headquarters in Saskatoon, but we have clients from all around the world doing a wide variety of different projects. So certainly it's a company that's global in its approach. We do a lot for the mining industry, and all sorts of aspects of the mining industry cycle. So we are available for all sorts of different things, and anything from extractions and things like that, and basically finding technological solutions and looking at environmental solutions, and basically we kind of work on what industry needs and providing what industry needs. So I'll get into the heart of the presentation here. So basically what I'm going to talk about is just some basics on radiation and radiochemistry. Then we'll talk a little bit about how things how radiation and radioactivity kind of impact operations, and then also how it's used in closure and remediation, and then turn it back over to Steve to talk about the radioactivity in mineral exploration. So yeah, I think everybody's aware that radioactive elements, they come about in many different mining operations. Of course, there's certain mining operations like uranium mining, where those elements are, uranium is mined specifically for its radioactive properties. But there's also other radioactive elements like, or radioactive minerals like potash, which just has radioactivity naturally associated with it. And really in any type of mining, there's going to be some traces of material in the, in the waste rock or the effluents or things like that. There's going to be traces of radioactive material, and that can sometimes pose issues. So there's usually some type of monitoring for radioactivity. And throughout this presentation, I'll probably use a bit of, sort of technical terms. I often talk about radionuclides or radioisotopes, which are, of course, radioactive elements. Sometimes I just refer to them as isotopes. Of course, they're stable isotopes too, but in general, I'm usually talking about radioactive things. So if I'd say isotopes, I probably mean radioisotopes. One thing I think most people are aware of, but in case you're not, a lot of the naturally occurring radioactive elements like uranium and thorium, they will decay, and they'll decay into other radioactive elements. So usually they'll go through a series of decays. So essentially they can decay into, more than a dozen different elements that are all in turn radioactive. And they'll have different, of course, different chemical properties because they're all different elements and things like that. And each one of those decay processes is going to emit some radioactivity, either in the form of an alpha particle or a beta particle or gamma radiation. There's other types of radiation as well, but we're not going to be looking at anything like that here. And one of the things that's important to note for from a radiochemistry perspective is that those emissions, the type and the energy of the emission is characteristic of a particular isotope. And those emissions, of course, they'll have their own characteristics. So the gamma radiation, for example, is pretty highly penetrating, and it can, go through a lot of different materials. Alpha and beta particles, they're much easier to stop. But of course, an alpha particle is, is a very energetic particle, and although it's easy to stop, it does release a lot of energy when it does get stopped. So from a perspective of hazard, if something is, if it's an alpha particle and if it's ingested, then that's kind of biologically the most damaging. So as I mentioned earlier, in radiochemistry, it's sort of a unique branch of chemistry, and we can use the emissions of those various radioisotopes to help identify what the isotopes were. So you can look at the energy of what was emitted. Techniques can be really, really sensitive. And lots of times in radiochemistry, what we'll do is we'll go through a process, chemical process, isolate sort of the elements of interest, and then we can do a determination. So on the screen there in the picture, there's some alpha counting going on. So we're basically we've isolated, in this case, it's thorium, and we've got it basically on that filter that she's putting in the instrument, and we're going to count the alpha emissions. We'll be able to tell from the energy of the alpha emissions which isotope of thorium it is. So it could be thorium-232, 234, or 230, and we'll be able to determine that from the energy of those emissions. One of the things is that with longer half-life material like uranium, which has a half-life in the billions of years, it's almost, sort of semi-stable in the sense that it sticks around for a very long time. And you can characterize those elements in terms of, what we normally think of parts per million or things like that. But when you're talking like stuff with much shorter half-lives, things like radium or even shorter half-lives than that, these become materials that we would say have a higher specific activity, and they can release a significant amount of radiation from a very small mass. So when we're doing radiochemistry, we typically quantify that material in terms of becquerels, and there's a relationship between the becquerels and the sort of the micrograms or whatever. There's kind of a relationship between the mass, but it's usually much more conducive to say it's so many becquerels per gram, or it's easy for people to sort of get the concept of, say, parts per million. But if it's when you're talking something that the mass is so small and you're saying it's like 1 × 10⁻15 grams per gram instead of a microgram per gram, it's pretty hard to visualize. So it's easier to characterize it in terms of becquerels. So as I mentioned earlier, that it's radioactivity is something that's kind of impacts most mining operations. There's the MDMER, which regulates the releases of radium-226, which is part of the uranium decay series. So it's uranium is kind of ubiquitous in soils and small quantities, and so you're going to also, if wherever you find the uranium, you're also going to find radium. And radium being an alpha emitter, it ends up being having more stringent controls. And smaller quantities can present issues. So so basically, the it's controlled under those regulations, and pretty much all mining operations have to look for that. Of course, if you're looking at uranium mining, then you're monitoring for a number of other radioisotopes. And then other things that can happen in different, so that's sort of a, radium, I gave the example, is something that can happen in any kind of mining operations, but there's other radioactive materials, the other things that are in that uranium and thorium series of decay elements that can present issues in different industries. So not even just mining, but if you think of oil and gas, if you think of natural gas, for example, it's found underground, and then in the ground, of course, there's going to be, like I say, traces of uranium. Uranium's going to decay into different radioactive elements. One of those radioactive elements that it decays into is radon, which is a gas. So what will happen is the radon will emanate out of the ground and mix with the natural gas and become kind of part of that natural gas. And as the natural gas gets moved around, that radon is going to further decay into something that's that is a solid particle again. It's no longer a gas, and it will come out of the gas, and it could accumulate on pipes and things like that. And so you can end up with what they call like little hot spots or things like that, where the radioactive elements are accumulating. And so these industrial processes can sort of lead to unexpected or unanticipated concentrations of radionuclides. So there's a term for that, a T norm or whatever, technologically enhanced naturally occurring radioactive material. So it's something that can catch people by surprise. But of course, like I say, there's lots of people in lots of different mining sectors that can be impacted and need to test for radioactivity. And there's often, we find a lot of people are concerned, well, how do I ship you a sample? What's going on? How can I get it? Most of the uranium mining people, they're pretty familiar, and they have their UN numbers, and they're pretty easy to know how to ship things off. Other clients less so, so it's always a bit of a question, but we're always available to, we can accept those materials, and we're always available to answer questions or things like that. Interestingly enough, there's kind of a cutoff for the transport of dangerous goods regulations at 70 becquerels per gram. And it's not always possible to know, if something is classed as radioactive when you go to ship it, because it's pretty hard to know what the concentration is before you ship it for analysis and that sort of stuff. But the 70 becquerels per gram is interesting because if you look at something like potash, the radioactivity associated with it is just below that threshold. So essentially potash can be shipped, without having to comply with transport of dangerous goods regulations. Yeah, so this I just wanted to mention as that we are available to support clients with various needs and questions in terms of shipping samples and stuff like that. So sometimes samples can have sort of unexpectedly high radioactivity. So we've seen that oftentimes in sediments where the radioactivity kind of accumulates and you're not sort of expecting it to be radioactive, but and it ends up being a lot higher radioactivity than you might expect. So this last sort of section I want to talk about just how we use sort of radiation is in, in sort of assessing situations and things like that. So one of the projects that SRC is involved with is the cleanup of abandoned northern sites. And this is a number of uranium mines that were opened and operating in the 1950s, when there wasn't really a lot of regulation, and essentially when these mines finished up, they just closed and left, and there was no sort of shutdown or anything like that. So this led to a lot of safety and environmental issues, and so right now SRC is working currently to try to get these sites so that they're remediated and safe, and essentially we want to get them to to be able to return the sites to provincial control under the institutional control program, which I'll talk a little bit more about in a slide or two. But I just wanted to point out that, when we first initially got this project, is kind of like, what's the extent of contamination? Because these mines were abandoned, so the tailing piles were just sort of left there, and you can imagine these radioactive tailings just kind of like blowing around. Like dust in the wind, sort of blowing around. So it's like, how far did this contamination go, and where does the sort of the contamination end in that? And so we were able to do gamma surveys, basically outfitting someone with a backpack and a Geiger counter to go around and just measure the radiation through the whole area and find out, where basically the sort of the hot spots were, where the sort of the edge of the contamination is, and all that sort of stuff. So that initial characterization of what the problem is. And then there was, of course, follow-up during that process as you do different remediation efforts and fix things up and install soil covers in that to kind of block some of that radiation, as well as ensure that things are meeting the criteria and that it's safe for when it's done. Yeah, and then, as I mentioned, it's kind of a unique, Saskatchewan has a bit of a unique thing called the Institutional Control Program, which began in 2005. And under this program, it's kind of nice because it gives the sort of mining operators the opportunity to sort of, once you've remediated to the point where you can turn it over to the province for that, sort of long-term monitoring, and you can basically turn it back to, it becomes Crown land again and things like that. So it's just sort of that formal regulatory process, and basically the province will essentially say that, okay, this is, everything is well controlled, and we can take over control of this and do that sort of, long-term intermittent monitoring to make sure that it stays under control. So that's essentially all that I have to say. And if you've had questions, I hope you've written them down. But yeah, just to summarize, the key points, I guess, or key takeaways is that the radiochemistry techniques, they're pretty sensitive, and we can often see some pretty low levels of things. In that the radioactive materials can pose some they can pose a concern environmentally and health-wise and things like that, but oftentimes the radioactive properties, you can use those to sort of help find them or help identify them and things like that. So some unique advantages there. So that's pretty much all I got. My contact information is there if you have some questions that you think about after the presentation or whatever, and feel free to reach out. And now I think I'll just switch this presentation over to Steve and see how that goes. Okay. Steve, I think you're on.
All right. Okay. So I'll be talking about radioactivity specifically applied to mineral exploration, and look at some of the unique things that can be done from an obvious standpoint, like uranium, and it's a little less obvious in some of the applications of radiochemistry in mineral exploration. So as an overview, we look at some of the important radionuclides. I'm going to be like Jeff. Anytime I say isotope, I generally mean radioactive isotope. There's a huge amount of information on stable isotope geochemistry, but I'm not going to touch on any of that. In fact, radioisotope geochemistry is also a major topic. So we'll be kind of lightly brushing over the surface of a lot of that. And then we'll look at applications in uranium mining and exploration, rare earth element deposits, and applications in copper porphyry systems and ore sorting as a kind of an emerging technology that we're working on at SRC. So important radionuclides in geochemistry include primarily uranium and thorium, uranium decaying to isotopes of lead, so U-238 decays to 206 lead, 235 to 207 lead, and 232 to 208 lead. We can measure all of those isotopes and get an idea of where the lead is coming from, if it's a predominantly thorium source or uranium source. And we can measure other isotopes as well, looking at like rhenium and osmium, potassium to argon. That's the one that's most important for potash, where you have high potassium concentrations. Rubidium to strontium, samarium to neodymium, and lutetium to hafnium. These are all commonly used in various geological contexts. I'm not going to talk about the lower ones, simply because there's just not enough time. There's massive, huge topics here. The half-life for a lot of these is in the hundreds of millions of years. Uranium-235 is about 700 million years. 238 is about 4.2 or 4.4 billion years. Thorium is much longer than that. Rhenium osmium is something like the age of the universe, is still in the first half-life of 187 uranium. So looking at an application for unconformity uranium deposits, these are very interesting deposits. They are the highest grade uranium deposits in the world. They occur in not very many places, primarily in Canada and Australia. But the most important and significant ones are in Saskatchewan, specifically in the Athabasca Basin. And that's because they are the highest grade. This rock on the screen here is about 80% uraninite, that's UO2. This rock will most definitely kill you if you eat it or lick it. I would strongly advise staying away from these things if you can, unless of course you're exploring for uranium, in which case this is an incredibly important sample. So as Jeff mentioned, uranium decays by alpha decay primarily, and then its daughter products are gamma emitters. So when we're doing a gamma survey for uranium, we're looking at the daughter products, not uranium itself. And that's fine as long as it's in what we call isotopic equilibrium or secular equilibrium. And most commonly, that's the case. So you can use gamma spectrometers or gamma detectors like Geiger counters just to detect these. The original exploration for uranium in the province was done by surface surveys using Geiger counters. So basically, like walking around with a Geiger counter when things start ticking, grab a rock and take that back to the lab. With Saskatchewan's high-grade uranium deposits, there are special considerations that need to be taken into account when we're providing support for this exploration type. Firstly is the safety of the people involved. So all of our samples that we receive are scanned for radiation, even if we know it's not radioactive. Just the SOP for safety requires that every sample is scanned for radioactivity and then sorted accordingly and treated according to its radioactive intensity. In geophysics, we have downhole gamma surveys, and this is used to identify the range of the deposit or how far out it goes from the original area of exploration. And often what happens is in the Athabasca Basin is because the concentrations are higher, most uranium deposits will be like 0.1% or less than 1%, but you can have zones of up to 20 to 40 and 80% uranium. So this requires a unique calibration so that the detectors aren't constantly being saturated. And we provide support with that using what are called test bits. That's this old black and white photo here. These are basically simulated holes or drill holes with known uranium concentration that can be used for calibrating geophysical gamma detectors. And of course, we have specific standards that are high uranium concentration and all the methods for digestion and safe handling as part of our SOPs in the geoanalytical lab. So I'm going to move to rare earth elements. This is one that's obviously quite important lately. but the radioactivity associated with rare earth element deposits is commonly overlooked or just not considered. This becomes a major problem when the target for the rare earth elements is monazite. Monazite is a rare earth element mineral. It can contain, and typically does contain, between 4 and say 15% thorium as thorium oxide. 10% is a pretty common number that you'll see for the amount of thorium in monazite. So there's that. It can also occur in secondary minerals. As monazite breaks down in a geological time frame, it turns into apatite, allanite, and can also include thorionite and thorite. Those are thorium oxide and thorium silicate. So those can also be concentrated in there. The idea of making a mine is that you want to concentrate the elements that you want to extract. So as you're concentrating rare earth elements, you also are concentrating the thorium. And so those are the technologically enhanced, naturally occurring radioactive materials that Jeff was talking about earlier. That's a major consideration that needs to be accounted for in rare earth element deposits. And these also, because of the radioactivity, require the same safe handling or similar safe handling procedures and licensing as uranium deposits, uranium ores. Okay, taking a wide turn to copper porphyries. Copper porphyries are not radioactive. Well, slightly. I mean, there's be a small amount of uranium in there, but certainly not being mined for uranium. What's being done in copper porphyry exploration is looking at UPB, uranium lead dating of zircons. Zircon is zirconium silicate. It includes small amounts of uranium while it's crystallizing and excludes lead. So it becomes a chronometer or like a clock that starts ticking as soon as the rock solidifies. And by measuring the isotopes of uranium and lead in the zircon, you can back calculate how long it's been decaying for. And then using some fancy math, you calculate the age. And then taking zircons that are found in sediments. So these would be zircons that erupted in a magma or lava, typically magmas, and then get exposed to the surface. Those rocks then erode and get incorporated into sandstones and other sediments in the area. These are called detrital zircons. So these detrital zircons are all collected and then analyzed. And what you typically find is multimodal populations of zircons. The example I have here is a bimodal population, one age at 296 million years, so something like Devonian, and then an Eocene age of 45 million years. And these have geological implications. The older zircons are from barren basement rocks, so these would be just older eruptions that didn't include any copper, whereas the younger ones are associated with copper mineralization. And knowing that you have zircons in an area of known copper deposits associated with the age of copper mineralization, then you can go to a second stage of looking at the trace elements in the zircons and use those to identify if these are associated with copper mineralization or not. That's the example shown here from northern Chile. There are some very famous mines in this area. I'm just going to draw attention to like El Salvador down here. So the El Salvador mine is 40 million years. And the zircons that are shown here, these are called porphyry indicator zircons. And the mine has a large proportion of those favorable indicators, whereas a non-mineralized area has none. So that's how you can use radioactivity in a specific sense to calculate age, to look at copper porphyry deposits or for exploring for copper porphyry. One other use for zircon dating in copper porphyry deposits is to look at the duration of mineralization. So each porphyry event will have a time signature associated with it. This is from the Bingham Canyon mine in Utah. There are 4 distinct events, and they have a specific duration. These are from different zircon populations and different magmatic intrusions. The EM one is barren, so no copper associated with that one. And then these final 3 have a significant amount of copper. And studies of copper porphyry deposits, specifically with respect to zircon dating, shows that with the duration of mineralization, as that duration is elongated, then the amount of copper that the porphyry system contains increases. There's a pretty strong correlation between how many and how long those magmatic events are and the amount of copper deposited, which makes sense. The longer you have hot fluids moving around, the more copper can be mobilized and deposited into a deposit or a favorable area. So knowing that you have zircons of an age associated with copper porphyry events, and knowing that they've been around for a long time produces some pretty good indications you are looking at a great copper porphyry deposit. So something more emerging is ore sorting and some ore analysis techniques that are relatively new. I mean, PGNA, like neutron activation, isn't new, but using it in ore sorting is relatively new. We can look at radioactivity two ways in ore sorting and in characterization, and that is intrinsically radioactive, so rocks that already contain uranium and thorium that are radioactive themselves, or we can induce radiation in these rocks. That's done by it's done by thermal neutrons in the PGNA environment. So the sample is bombarded with neutrons, and then it creates short-lived isotopes or isomers. And then as these nuclei relax back to their ground state, they emit gamma photons that are of a known energy. And then using gamma spectroscopy, you can actually measure that. One of the most interesting things, I think, in my world of analytical geochemistry is the Chrysos photonassay. This is a relatively new development. It's using a linear accelerator to generate high energy X-rays. And those X-rays are used for activating gold isomers in a sample. And those isomers are just really short-lived isotopes. They have a half-life of about 7.7 or 7.8 minutes. And you can measure the energy that's emitted from the gold, and that's proportional to the concentration. So it's a non-destructive gold assay that is looking to replace fire assay in a lot of applications. It's suffering right now a little bit because the detection limit's pretty high compared to fire assay, but you never know where it goes. It's an interesting machine. I'd like to see it in operation someday. Also, linear accelerators are just fun to play with. Looking at gamma spectroscopy. So Jeff mentioned that uranium and thorium have predictable decay chains. This is a sample measured in my lab using gamma spectroscopy. So we're looking at the gamma energy as related to counts, and we can identify the peaks that are occurring. We can see some pretty important things from the 232 thorium decay chain. So we have first X-rays that are generated. We can measure those. Those are not terribly interesting. But then we can also see gamma emissions from lead-212 and actinium-228 and thallium-208 as the thorium decays to lead. Interestingly, if you were to measure this long enough, you could actually see some of these isotopes decay. It's kind of fun. I mean, you know it happens, but seeing it in the lab is neat. We can use those gamma emissions to sort rare earth element ores. In the previous slide, what I showed you was a monazite sample, or a sample that contained about 20% monazite. And then if we use the gamma emissions from lead-212, like thorium itself doesn't have a significant gamma emission. It's an alpha emitter. So we use the gamma emissions from daughter products of thorium decay. And when thorium is closely associated with the rare earth elements, we can use that to correlate between the gamma emission and the total rare earth element content of the rock. Then using this information and the relationship between these two factors, you can design an ore sorting procedure that will accept anything above a certain count rate and then enrich the product in total rare earth element content. Kind of remove the waste and increase the grade of the material you're wanting to. The downside is when you're increasing the total rare earth element grade, you're increasing the thorium. So kind of got to be aware that you're also increasing the radioactivity of the samples as you're doing the ore sorting. One of the most obvious examples of gamma sorting is in uranium. Again, not using uranium directly because alpha particles are just difficult to detect outside of a very specific environment. They're blocked by just about everything. So we're using the isotope of lead-214. This is a strong gamma emitter, and we can correlate the gamma counts versus the assayed amount of uranium in the samples and can do the same kind of thing. So we can use this as a predictor of grade, or we can use this in an ore sorting environment where we would make a cutoff of a certain number of counts, and anything above that counts would be accept, and anything below would be reject. One example we studied for a client was increasing a grade from 0.1% to 5% with about a 60% waste removal. And in ore sorting, the goal is to remove as much material as possible so that your downstream costs are lowered, both in terms of economics and environmental impact. So in summary, natural and induced radioactivity is important in mineral exploration, and this is beyond the obvious use case in uranium. Thorium is going to become a major factor in considerations as rare earth element deposits become more important economically. Unique gamma signatures can be used to identify the source of that radiation, so we can look at the various isotopes of lead and know if we're dealing with a uranium or thorium system. And we can use uranium lead dating to give us more information about the specific geological environments and the importance that might have on predicting future grades or location of deposits. And gamma emissions, again, both induced and intrinsic, can be used to concentrate various ores. I didn't speak too much about PGNAA, but it's basically an induced gamma signature that can be used as a sort of an online or on-belt assay. Thank you for your time. My contact information is here, and I'll turn the time over to our coordinators.
Oh, thank you, both of you, for that. So maybe what we'll do is I have a couple questions that popped up with Jeff's presentation, and we'll start with those. So Jeff, is the cutoff of, oh gosh, sorry, BQ represents
Becquerel.
Becquerel, thank you. Is the cutoff of 70 becquerel per grams independent of the source? And are different sources more dangerous than others?
Yeah, so the 70 becquerel per gram is independent of the source. So it doesn't matter which radioisotope, if you've got 70 becquerels per gram. And in fact, like in a lot of cases, like say in uranium, you can have a whole bunch of different isotopes present. So all those isotopes together combined have to be less than 70 becquerels per gram. So that's why I said it's pretty difficult often to know if you're below that threshold or not. Without the analysis, it's hard to know beforehand. But yeah, what was the second part of the question there? I think
the second part was, are different sources more dangerous than others?
Well, I mean, from the, like that 70 becquerels per gram limit is like for the transport of dangerous goods, right? So that in the transport regulations, it's really, they're looking at, you're sort of looking grossly at the kind of exposure that people involved in transport might be exposed to. So you have like truck drivers or, handlers, material handlers, people like that, that kind of in a way are being sort of unwittingly, if you like, exposed to radiation. So it's basically, once you reach a certain threshold or whatever, making sure that the markings are in place so that they know that there's, okay, this is radioactive, whatever. If that makes any sense. Yeah.
Okay.
Yeah.
And can the radioactive dating be used to help understand geochemical fingerprint for the ore and differences in composition of co-occurring elements, like for example, gold?
Probably. Oh, sorry, Jeff. I assume this is for me since.
Yeah, that sounds like a question for you. For sure.
Sorry.
I think so, but you'd have to do enough background surveys to make that determination. With copper porphyries, this has been studied for quite a long time now. So I can't think of any reason why the same principle wouldn't apply to other deposit types. So I would assume that's the case. I don't know enough offhand to say if that's true or not, but geochemically speaking, the processes that form gold deposits or porphyry gold, porphyry copper are more or less identical. So I would say yes, with some hesitation.
Okay. And I'm not sure whether you can speak to this at, say, mine operations, but to what degree is there a radiation protection program in place to protect and monitor exposure to miners from radiation, especially for non-uranium mines?
Yeah, I'm not sure. I mean, I think lots of mines are getting more and more concerned with, the safety of their operations and stuff like that. So obviously, if it's a uranium mine, there's a lot of protections in place and monitoring or stuff like that. For other types of mines, there's probably no regulation stipulating what needs to be done. And really, I think a person can basically do an assessment of radiation fields or whatever within that mine operating environment to know if there is any kind of particular hazard or if any extra precautions need to be taken. Because there are some mines, I think, older abandoned mines that are known to have like high radon concentrations and things like that. So it could be a problem in any sort of mining environment, but I think it's sort of up to the mine to investigate that and determine if it is a problem and take appropriate action, I guess.
Okay. Now, this one I think is for you, Stephen. Can the calculation holes be used to calibrate satellite monitoring?
Maybe. I don't know if you could detect gamma emissions from a satellite unless you had an extremely sensitive detector. The background noise would be so high that you wouldn't be able to detect it. You could probably do it with airborne geophysics, more likely than satellite. I don't know of any technology that would be detecting uranium deposits from space, unless you're looking at alteration mineralogy, some other like secondary signatures rather than the primary signature. I don't think you can detect the gamma that far away from the source.
Okay.
It'd be interesting to see if even an airborne could detect it. Most likely, yes. Like a drone-based gamma detector might be able to pick it up.
All right. So can alkali metals like cesium be radioactive? And when they are present, do we need to make special precautions? And forgive me, CS is cesium, is it not?
Yes.
Yeah.
So like typically cesium is not radioactive, so it's not normally radioactive. But what can happen is when you're operating like a nuclear power plant, or if you have nuclear weapons that are, being tested or released or whatever, one of the radioactive isotopes that will be released is cesium-137, and that is, that radioisotope is a concern because it's it's a beta emitter, but it can be fairly, it'll behave like sodium, so it will follow along the food chain and be readily ingested by wherever it goes, kind of thing. So it is a concern environmentally. So when we have incidents like say Fukushima and things like that, there's a release of cesium-137. It's a shorter lived radionuclide. So like I mentioned in the presentation, you have a higher concentration of radioactive emissions from a very small amount of material. So that's why it can be problematic in events like that. And it is in fact one of the things that we will look for. Say for example, when people go to ship grain or seeds or things like that to other countries, countries will often have import restrictions, and they'll require a certificate that shows that the grain or food is not contaminated with any of these artificial radionuclides like cesium-137. And so that's one of the things we do in our lab, actually, is we'll analyze grains and confirm that there's no contamination with, say, cesium-137. But like I say, it doesn't occur naturally. It's a man-made isotope.
Yeah, cesium-133 is the only one that occurs in nature, and it's stable. Actually, cesium-137 is one of the funnest elements or isotopes to detect. It's used for detecting artificial aged wines. So pre-nuclear explosion wines would have no 137, whereas anything made after the 50s would have trace amounts of cesium-137 in them.
And I'm curious, Stephen, have you been called upon to
No.
verify such things? No.
No, but I'm always interested in unusual applications for analytical methods, and that's one of the ones that always kind of amuses me.
Right. So can physical ore separation process, can the physical ore separation process produce tenorm?
Yeah, in fact, that's a major concern for rare earth element deposits, because you are producing the tenorms. That's an unintentional occurrence. In uranium ores, it does, and that's what you want. So yes, sometimes good, sometimes bad. Well, always a safety concern, but usually by the time that ore sorting is being conducted, everybody has a good idea of how much radioactivity is going to be in the samples, how much thorium is present. So you can take appropriate safety precautions.
Yeah, so on that note, at what level is radiation exposure dangerous for human health?
That's a Jeff question.
Yeah, so that's essentially, I guess the main health concern for people in terms of exposure to radiation, like limited exposure, is really the main concern is a greater risk of developing cancer of some sort. And so essentially the higher your exposure, the greater your risk. So there's no sort of definitive number where, okay, at this much exposure, you're definitely going to have a problem. It's kind of like people that smoke cigarettes. Obviously people who smoke cigarettes, they're going to have, a higher risk of getting lung cancer. And but you still hear stories of, well, even my father-in-law, who smoked all his life and lived to 86 or whatever, but never got cancer or anything like that. But of course, there's just a higher risk. So there are, of course, limits. So if you are just like a normal person, there's a limit, and it's kind of a technical term again. Essentially, you get radiation exposure from different things, and you might have some occupational exposure. So people that work, say, here in my lab, we call them members of the general public, and we monitor their radiation exposure, and that's limited to 1 millisievert per year. If you work in, say, a different industry like uranium mining, or if you're working in a nuclear power plant or something like that, as part of your job, you sort of accept a higher risk of working with radiation, and so those people are governed by the Canadian Nuclear Safety Commission, and their exposure limit would be like 50 millisieverts per year. So that's even at those levels, it sounds higher. 1 versus 50, that seems like a higher, much higher sort of level. But even at those levels, the increased risk of getting cancer is like something like 1 in 1,600 or something like that, which is pretty small, considering that your normal risk of getting some type of cancer is on the order of 25 to 30%. So the increase from getting 50 millisieverts of exposure is not really all that significant, I guess.
So you mentioned how potash is just below the threshold for shipping. So what happens when you go over that, and like what is required in terms of the processes for shipping something that goes over that 70 becquerel per gram threshold?
Yeah, so essentially it's just, it's knowing what your material is and basically labeling it and shipping it correctly. The most common types of mining type of materials is usually associated with uranium mines where you'll be above that threshold and they'll ship it, as I mentioned, as like what they call an LSA or low specific activity material, and they categorize it as, 1, 2, or 3, depending on how much radioactive emissions are coming off of it. And it sort of avoids having to determine sort of exactly what the concentration or how many becquerels per gram are there per se. But the reason why that sort of cutoff is there is because oftentimes when people are shipping, say, like a medical isotope for nuclear medicine or things like that, which is done commonly, they'll know specifically how many becquerels or whatever that they're shipping, and they'll have a really good idea. But for naturally occurring materials, it's often really difficult to kind of know what you've got exactly. So.
Okay. Yeah, you mentioned it earlier, and it was just sort of someone commented on this, maybe not so much as a question, but just that rare earth elements are, and handling them requires more precautions than I guess other minerals. Is that?
Yes, rare earth elements themselves are not radioactive. Well, some of them are, but the half-lives are so long they're effectively not radioactive. But it's the associated thorium, and not all rare earth elements have associated thorium. Not all rare earth element deposits have associated thorium. So it's important to characterize that early on, so you can just make sure everyone's going to be safe and all things are going to be shipped according to the licensing that's in place.
Okay, great, thanks. And I think, so we've got one more here. What is the relationship between radioactivity measured in becquerels per gram and microsieverts?
Yeah, it's a complicated relationship. It's really complicated. So because it's all going to depend, we sort of alluded to the fact that the different radioisotopes have different energy of their emissions and things like that. So a particular radioisotope, can have a higher energy emission, and it can give you the microsieverts or millisieverts or things like that. Those are related to the dose or whatever that you receive or your actual exposure. And so if you have an isotope that has a higher energy, you're going to get a higher dose basically from sort of the same number of emissions, if you like. So it really depends. There's no sort of easy way to characterize that. And what will often happen is you'll get sort of radiation meters that will have a readout in terms of say millisieverts or millirem or microsieverts or whatever per hour. And that's based on a lot of assumptions. So they're making an assumption on the efficiency of the detector and sort of what sort of the energy of the emissions and things like that. So typically they use, I think it's cesium-137, which has the energy is kind of in the middle, so it's a sort of a good average, and they use that to kind of calibrate it and sort of assume that that's what you're going to be receiving. And then if you compare that to say, something like, emissions from say uranium ore or something like that, you're going to have some of those isotopes present that are going to have higher energy emissions and some that with lower energy emissions. So it sort of balances out, but like I say, there's kind of a lot of assumptions that go into that.
Okay, great. Well, I think I haven't seen any other questions pop up. So we've just got a couple more minutes. So I think maybe at this point, we'll just Just let everybody know that the questions asked will be compiled and sent to Stephen and Jeff if a more fulsome answer is required. All right, and again, thank you, gentlemen, for this.
All right, thank you.
Yeah.
And thank you, Jeff and Stephen, for that interesting presentation. I'd like to thank all of our attendees and ask that you please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed to you tomorrow afternoon. For more online presentations like this one, visit the CIM calendar of events on cim.org. And we look forward to seeing you at our next Solutions Exchange webinar. Thank you very much and have a good afternoon.
All right, thank you. Bye now.